very basic idea of continuity, which you all might know, which you all might have studied in your BSc first or second year. And so it starts with a very basic definition of continuity. We know that if we, from our childhood, we know that if we do not lift our pen and we can draw a curve without lifting our pen, then that curve will be continuous. But that idea is just a half idea, because when you go to higher classes or you go to college, this idea is something that is not worth it, because that is only applicable to domains that are connected. If you are talking about connected domains, then we can say that we can draw the graph. If we can draw the graph without lifting our pen, then that graph will be a continuous graph. So in the connected, it's fine. But if we talk about very general definition of continuity, the epsilon delta definition, then what is the definition? So this is the most basic idea of continuity, which will work for every type of domain, whether it is connected, whether it is not connected, whether it has limit points, whether it is isolated kind of domain. So what is the idea? It says that if a function is defined from a set A to real numbers, where A is a subset of real numbers, it can be a real number set or it can be a proper subset of real numbers, then we say that f is continuous in A, or at any point of A. Let's say C belongs to A. We say that f is continuous if there exists a delta for each epsilon. Okay, for all epsilon greater than 0, if there exists a delta greater than 0, says that whenever I say that my function, I can write this as whenever my function belongs to this interval, whenever x belongs to this interval C minus delta to C plus delta, whenever x is in the neighborhood of C, fx is in the neighborhood of f of C. So this is the most basic idea of continuity. So no matter how small you choose your epsilon to be, we can always find a del, so that whenever x is in the neighborhood of C, fx is in the neighborhood of f of C. Okay. So this idea is very theoretical, right? We cannot apply it to as many questions as we want to. So to extend this idea, we need many results to support. And those results we are going to study in today's class. Today's class is going to start from very basic. Don't worry that you won't be able to catch up with this. I will start from the very basic and we'll go to some good level of questions, okay? So if you're in BSc or you're in MSc or you're MSc pass out, doesn't matter, this class is for you. So this class will be helpful for JAM, CSIRNet or GATE or any other related exam. Okay, so this was the basic idea of continuity. I won't go much deep into that because I know you have the idea of, how do you graphically draw this. Okay, so you have C here, you have f of C somewhere here. Whenever you take the neighborhood of C, you get the neighborhood of f of C, something like that. You all have this idea. Okay, but how do we practically apply this kind of definition? Is that whenever we encounter a question, we'll have to figure out whether that point that we are dealing with, that we want to check the continuity of a function on, is a limit point of the domain of f, or not a limit point of the domain of f. So if it is a limit point of domain of f, you have a different criteria. If it is not a limit point of domain of f, you have a little bit different criteria. So let us talk about the first one, if C is a limit point of domain of f. So first of all, to check continuity on any point, your function needs to be defined at that point. So remember the idea I shared in last class. You were there or not, doesn't matter. Let me share the idea again. When you were checking for the limit of a function, you said that you will not include C. You said that x will not be equal to C. But here, while checking continuity, your x can be in the neighborhood of C or it can be equal to C. So specifically for limits, x should not be equal to C, because we are talking about the neighborhood of that point. If you're checking the limit at C, that point needs to be in the neighborhood of that, not equal to that. Okay, but when we are talking about continuity, we should talk about that point, and we should approach that one point from left or right, whatever limit side is applicable. We'll talk about this in detail in further lecture. So if C is a limit point of domain of F, first of all, it needs to be defined at C. Okay, if your function is not defined at that point, we cannot check continuity at that point, or we'll say that F is not continuous at that point. Suppose if I give you a domain, let's say 0, 1 to R, and if I ask you f of x is equals to x squared, whether this function that I've given you is continuous on x is equals to 2, what will be your answer? You cannot check at that point because at x equal to 2, your function is not defined. So function is not continuous at that point. So first and foremost condition is function has to be defined at that point. That means that point should be a part of the domain of that function. The second criteria is that the limit of that function at that point should exist. Now you might be confused about whether this is left-hand limit or this is right-hand limit. Well, both. You know, whenever you can approach from right hand side and left hand side, you say both RHL and LHL, they should exist, they should be equal. But when you can only approach from one side of that function, then you'll talk about only one side limit. So it depends on the context and the question. And the third part is, we'll talk about it when we discuss some examples. And the third part is limit extends to C, f of x is equals to f of C. Whatever limiting value that you get at that point should be equal to the functional value. Okay, you can talk about limits only if you have that point as a limit point of the domain. If you do not have a point, that point as a limit point of the domain, you cannot talk about the existence of limit. You cannot find limit. You cannot talk about limit. So for 2 and 3, we don't have any criteria. If only the function is defined at C, then in case C is not a limit point of domain of F, then we just check if the function is defined at C, cool. If it is defined, we'll say that F is continuous at C. Okay, so two different criteria. C is a limit point or not a limit point. If C is a limit point, you have to check 3 conditions. If C is not a limit point, if C is not a limit point, you just have to check whether F is defined at that point or not. So what I really want to talk about is, let me give you 2 different examples. Okay, on the right hand side, I'm writing 2 different examples. In case 1, I can have any example like from R to R, and someone asks you at x is equals to 1, does this function is continuous? So you say yes, this function, sorry, I should define this function on this domain, R minus 0. So you will say that this function is continuous at x equal to 1, okay? But you will check for 3 conditions because x equal to 1 is the limit point of the domain. But what if I give you some function like this? F of x is equals to 1 by x. Now in such a case, you don't have any limit point in this domain because this domain is a domain of isolated points. This complete domain do not have any limit point. So if I give you some, random point at x is equals to 7, if I ask you whether this function is continuous or not, you won't check for the limit point because that is not valid here. You'll just check whether this function is defined at x equal to 7 or not. It is defined. So you will say that yes, this is continuous at that point. But if someone asks you, let's say, tell me if this function is continuous at x is equals to -2, then in that case, it is not continuous because it is not defined at that point. You don't have a value corresponding to -2. Okay, so these are 2 different criteria. These are very basic things that you should know. I hope you know it already. If you didn't, I hope you know it now. Okay, if you have any little doubts regarding the topic, you can ask me now because I haven't planned the lecture very large because I want you to take your doubts, side by side, because a very long lecture will not help you in learning. So I've kept the lecture length to be small so that you can learn more. So let's talk about this specific example. How do you check continuity in any interval? So if I give you this interval, so this is your domain, and if I ask you, how do you check the continuity in this interval? All these things are kind of theoretical because these are not going to help you in questions directly, but you need to know the concepts while solving a question because these basic things need to be clear in your head. So that's why I'm explaining you. Okay, so this is the domain that has been given to you. If you want to check the continuity on this interval, what you will do? For all the inside points except A and B, for all the inside points, you need to check both left hand limit and right hand limit. Suppose there is a point, let's say between A and B, there is a point C. If you want to check the continuity at C, what you need to do, if you need to approach C from left and approach C from right. So you need to check both LHL and RHL for C. So I have written this. At all other points, you need to check both RHL and LHL. Let's talk about what you will do for x is equals to A. See, for x equals to A, you can only check from the right hand side, right? Because you can only approach the point A from the right hand side, because on the left hand side, there are no limit points. There are no points to approach. There are no points of the domain to approach to A. So you can only check the right hand limit for A. Okay. So for A, we'll check the right hand limit is equal to the functional value or not. These are the things you'll do after you have confirmed that your function, the limit exists and the function is defined at that point. So after checking those 2 points, you'll check for the third one. So for the third one, you'll check the right hand limit. Okay. So what you will do for B? Can anybody tell me how to check the continuity of F at B? What steps do I need to take to check the continuity of F at B? Can anybody answer? It will be great to have an interactive session because it will help you a lot. Okay. Anybody? Okay. So did you notice that B is not a point of the domain? Sorry. Just a second. Left hand limit at B. Okay, someone is saying left hand limit at B. Okay, let's see. You can unmute yourself and answer because I'm not looking at your messages because that will waste a lot of time. I'll have to change windows. Okay, it will be better if you just answer for 1 or 2 sentences. You unmute yourself and answer. Okay, I want it to be an interactive one. So for B, if you notice that B is not a point of domain. So if it is not a point of domain, you'll have to remember that B does not lie in the domain. So the function is not defined at B. You didn't watch it carefully, but B does not lie in the domain. So you don't have to check. Suppose if I had written here the closed interval B, then in that case, you'll have to check for left hand limit. But in this case, B is not in your domain. So in that case, what you can do is you can check the functional value does not lie at B, but the limiting value lies at B. So what you can do is, I forgot to write here, you can check the left hand limit for B. Because the functional value, the function is not defined at B, but the limiting value exists at B. I mean, the left hand limit can be checked at B and you'll have to check whether it exists or not. Okay. So you'll have to check it. I forgot to write here, but you'll have to check it. You no need to check the functional value at B. No need to equate the functional value and the limiting value, but you'll have to check whether the limiting value of B exists or not. Because in case of limiting value, the point itself need not be a point of domain. So here B is not a point of domain, but you'll have to check for the limiting value. So these are, different criteria that you will use when you will be given a domain as an interval or any set. I gave you an example of natural numbers. I gave you an example of R minus 0. So you have different scenarios. So these scenarios should be clear in your head. Okay, let's do a quick exercise. Take out your pen and paper and try to solve this question. If the given function is continuous, I want to ask you, what is alpha? I want to know what is alpha. So alpha is some value of this function at 0. I don't know what alpha is. I want you to answer me. And this function, this brackets right here denote the floor function or the greatest integer function. So this function is greatest integer function. So can anybody, I'll give you 1 minute because this is an easy question. After that, I'll discuss. If somebody has any idea after 1 minute or some solution, they can come up with this and then we'll discuss it.
Zero.
Okay, somebody saying 0. Let's have more answers.
1.
Okay, there's 1 also. I'm sorry, the one.
Sign 1.
1 and
Sign 1.
sign 1.
Sign 1.
Interesting. We have 3 different answers already. Okay, sign 1. Someone also said sign 1.
Sign 1.
Okay, many answers for sign 1. Okay, shall we start discussing? So you might be mistaken in solving, the calculative part, but you understood the idea, right? I gave you a continuous function and this was its value for x not equal to 0 and this was its value for x equal to 0. So you got the idea that f of 0 was equal to alpha. You just needed to know what was the limiting value of this function, right? And if you were able to find the limiting value of this function, you could equate the limiting and the functional value because the given function is already continuous. So continuous function, limiting value and functional value both are equal. So you'll just equate. So you just needed to actually, this is not a continuity question, this is a limit question. But since we have done limit portion, I can hope that you can solve this question. Same limit x tends to 0. What we needed to solve was minus x square by minus x square, greatest integer function. So whenever x tends to 0, so whenever x tends to 0, what is going to be x square? It is always going to be, limit x tends to 0 means very small positive or negative quantity. You can approach from the left or from the right. Okay. So in any case, whether you approach from the left or the right, x square is also always going to be positive. So let's say it's very small value, 0.0001, let's say something like that. Okay. So whenever you apply negative in front of this will be a negative value. But if you take the greatest integer function of a negative value, what will it be? Will it be 0? No, it will be minus 1. So the numerator is going to be sine of minus 1. Okay, in any case, because x square is always positive, minus x square is always negative, a very small negative quantity. And that very small negative quantity in that floor function is going to give you minus 1. And same will be for the denominator. So you'll get minus of sine 1 divided by minus of 1. So you just cancel it out and you get sine of 1. And that's the correct answer, which was the majority answer in our class. So that's how, you solve a very basic question. This was a question to make you active. Just that. I know it's a very easy question, but it was just to make you a little active during the class. So we all know about discontinuities, right? We knew about continuity, but what about discontinuity? Whenever we talk about a positive, we'll also have to talk about a negative. If you're talking about continuity, there has to be a concept related to discontinuity. So there is one continuity which is jump discontinuity, which is of two types. First kind and second kind. Hoping that you know these concepts already. I won't take much time here. Okay, discontinuity of first kind and discontinuity of second kind. So the discontinuity of first kind says if the right hand limit of the function exists but is not equal to f of a. The right hand limit or the left hand limit, they might not be equal, or they might not, the left hand limit might exist, or it might not be equal to the functional value. Anything it could be. The function is said to have a discontinuity of first kind from right if the right hand limit is not equal to the functional value. In jump discontinuity, the left hand limit and the right hand limit exist and are finite but not equal to each other. Okay, so as I said, any of the limit might not be equal to the functional value, or they might not be equal to each other. So this is your discontinuity of first kind. What is discontinuity of second kind? A function is said to have a discontinuity of second kind if, you know, the left hand limit or right hand limit, इनमें से either one of those do not exist, right? Either if neither left hand limit nor right hand limit of a exists. It could be, you know, something like if I ask you limit x approaching to 0 sine 1 by x. So when I ask you this limit is an example of limit not being exist. So this is an example of discontinuity of second kind in such a case. So removable discontinuity, obviously, then as the name suggests, removable discontinuity says that if you have a function, let's say sine of x for x not equal to 0, and for x is equals to 0, you have 1. You have defined a function with the help of sine x, which is something different from sine x. So the limiting value of this function at x equal to 0 is obviously 0, but the functional value of this function at x equal to 0 is 1. So if you can change something in this function and make it, if you can remove the discontinuity and make it continuous, yes, we can do it. If we redefine the functional value, or let's say keep it same, if we can redefine the function with the help of this by changing the functional value, let's say x equal to 0, x not equal to 0. So in that case, this will be called a removable discontinuities. Discontinuities will be helpful, little bit helpful for you when we deal with the concept of monotonicity and intermediate value property in our next part of this lecture. So this was all about the first part of this lecture. If any one of you have any doubt regarding what we have discussed, you can ask. Then we'll move on to the next part where we'll discuss some results. Allow me to move, or rather, if you have any doubts, you can unmute and ask. Okay, so I hope you don't, I hope you're clear. So if you're not having any doubts, let's move further. So we'll talk about some very important concepts related to continuity, which you must know while moving to questions. So first of all, we have boundedness theorem. So what does this theorem says? Is if f is a function from any interval to R. So look at this interval. This is a closed interval, and this is a bounded interval. And f is continuous. So f is defined on a closed and bounded interval. On closed and bounded intervals in real numbers, they are called compact intervals or compact sets. Okay. If you have a function defined from such an interval to R, which is continuous, then f must be bounded. That means the meaning of this line is that the range of f will be bounded. F is bounded means the range set of F will be bounded. Okay, whatever the range set will be, that will be bounded. And the other thing is that F will attain its supremum and infimum. So since the range set is bounded, so it will be bounded not like this. You know, you have also, suppose the range set of F is this. In this case, what is the supremum of this set? The supremum of this set is this. And the infimum of this set is this. But in this case, you cannot attain the supremum and infimum. That means the supremum and infimum should lie in that set itself. But in this case, it doesn't. So F will not have a range set like this. So what kind of range set can F have? So in such a case, if you want to have a range set, you will have to have something like this, a closed and bounded range set, wherein you can say that this is the infimum and this is the supremum. Okay, something like this. So what if F is not continuous? You know, if I remove the condition of continuity here, what will happen? Can you think about it? So if I remove this condition that F is not continuous, will F stay bounded? Let's have a look at an example, because you can only understand the concept if you try to, you know, try to experiment with it. Let's try to define a function. Let's say I have defined a function x belongs to open 0, closed 1. And for x is equals to 0, I am saying this. Okay, so my function is defined from closed interval 0, 1 to R. What is the range set of this function? I want to ask you. Can anybody tell me the range set of this function F? Can anybody tell me? Will it be bounded? I hope I'm audible.
No.
It will not be bounded. If anybody can tell me the range set, that will be good. So let me just write
Closed
range set.
1, open infinity.
Closed 1 to open infinity. This will be the range set, and this is an unbounded set. So you see the difference. Why did this happen? Because this function was discontinuous at x equal to 0. Even discontinuity at one single point led to what? Led to unboundedness of this range set. So you see why these conditions are important. These conditions are very important. And if you remove the condition that F is not, if you remove the condition of closeness here, okay? And if I keep the condition of continuity, what if the domain of F is not a closed interval? So I'm removing the condition of closeness here. So let me define a function here. 0, 1 to R. Okay. Let me define a continuous function here with the same example, similar kind of example. F of x is equals to 1 by x. This function is a continuous function, but again, the range set of this function is again unbounded. Okay. Right. So we got the idea. Why I'm explaining this to you, all these things, and not moving to questions, is because whenever you are doing analysis, whenever you're doing the real analysis, it is very important to, you know, experiment with the conditions. Experiment by removing one condition, by adding one condition, by thinking about contrapositive, converse, and things like that. It is very important to think, you know, basically in pure mathematics, you'll have to think. So there is a very general idea. Rather than boundedness theorem, we can extend this idea to this first point. A continuous function maps a compact set to a compact set. Whenever you have a compact set in domain, in the range set, you're also going to get a compact set. So yes, something like this, if you have something like this closed and bounded kind of domain, you can also have a domain like this, AB union CD. This is also closed and bounded. But in result, you are going to get a compact set. So compact set on the left, you apply F and you are going to get a compact set in result. That can also be a union of, closed intervals and bounded intervals. That doesn't matter. Something like EF union GH, something like that. But it has to be compact. And whenever so this idea is related to boundedness theorem. This is a general idea of the boundedness theorem. Why I'm saying that this is a general idea is because in the boundedness theorem, you had just one interval, but now I can write as a matter of compact set, I can write a union of intervals. So this is a more general idea. So the second idea is related to connectedness. If you map any interval, if you take any interval, it will map to, and again, another interval. So if I is an interval, the range set f of I is also going to be an interval. So interval maps to interval, and why I'm saying intervals instead of connected set is because in real analysis, in real numbers in function of one variable that we are covering, all the connected sets that you have are intervals. Now you might be thinking that this is not an interval, but well, this is also an interval. This is an interval of this type. Closed interval from A to A. So the singleton set is also an interval. Phi is, although phi is also an interval of this type, open A to A. A can be any point. So there you have only three types of sets in when you're talking about connected sets: singleton, phi, or this non-empty kind of set. So remember the idea. Connected always maps to connected. And always, 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 phi can never be the domain of any function. You need to remember that phi can never be the domain of any function because the idea of a function is to have an input. But when you're you're substituting phi instead of a domain, you don't have an input. So I'm telling you small little things. I hope you have the ideas already in your head, but let's try to cover everything that we come up with. Okay, let's talk about this question. If AN is a sequence of, I want to give you 1 minute to use your head, solve this question and tell me an answer. Okay, 1 or 2 minutes will be fine for you, I think. Let's solve this question. This was asked in JAM 2015. If N is a sequence in closed interval 0, 1, f is a function from R to R. It is a strictly increasing continuous function from R to R. And they are asking what will be this sequence, f of AN. It will be increasing, bounded, convergent, or none of these. Even if you're not able to solve it, it's important that you think. And if you were able to solve it, then that's good. But it's important to at least think about a question before you just jump on the solution itself.
I am increasing.
Okay, someone is saying increasing. Okay, I have one answer for increasing.
Bounded.
Someone is saying bounded. Okay, very good. So anybody has this 3 or 4 as an answer? Okay, let's jump on to the solution. You might all have the, little bit idea of this question, whether wrong or right, but let's solve it. So first of all, they are saying that AN is a sequence in 0, 1, closed interval, and f is strictly increasing continuous function. So let me suppose, as I do not have any idea on how to solve this question, so let me take an example. So that is the most basic idea on how to start questions. Whenever you encounter a question in exam, you should have enough number of examples in your bank of examples that you can apply on different kind of situations that has been given to you. You should have enough number of examples to apply, so that you don't jump onto results or anything, because directly jumping onto results will not give you the fruitful results. So first of all, whenever you're doing pure mathematics, jump onto counter examples to cut one or two options at least. So f of x is an function, let's say x. This satisfies the criteria that it is defined from R to R. This is strictly increasing, and this is also continuous. So f satisfies whatever has been given in the question. Okay, and let me take an as to be 1 by n. This is very common sequence, and this is a very common function. I haven't taken any horrible kind of examples. Very simple and easy examples. So now f of an will be what? Since f is an identity function, it will be 1 by n. Now they are asking, what about this sequence? Is it an increasing sequence? No, this is a strictly decreasing sequence. So first option is incorrect. Why I'm able to cancel this option is because I've taken one example for which first option is not as satisfying. Okay, so even if an option does not satisfy one example, it will be cancelled out. But if it satisfies one example, it will not be cancelled out. But because it might not be satisfying other example. Okay, you can cross off the options with the help of counter example, but you cannot tick the options with the help of counter examples. So f of an is bounded, second option. Second option seems true, but I will not take it, okay? Because I don't know if it's correct or not. Third is saying convergent. Yes, it also seems correct. Fourth is saying none of these. I don't know, maybe. So I'm able to cut only one option with the help of this example. If I take an is equals to, let's say, 1, 2, 1, 2, 1, 2, something like this. And if I keep the function same, what will happen? F of an will become, I've taken simple oscillating sequence. F of an will become 1, 2, 1, 2, 1, 2, something like that. In this case, let's go back to our options. Yes, please. Anybody has any doubt?
Say sequence an is a sequence in 0, 1. Closed interval
Okay,
0,
sorry.
1. So
We can take 1, 0, 1, 0. Okay. Yeah, very good. You guys are attentive, that means. Okay. So f of an is increasing. No, not at all. I've already cut that option, so I don't need to care. Is it bounded? I cannot cut this option because it satisfies. Is it convergent? No, it's not convergent. So I can cut this option off.
no, it's not coming.
I'm confused between whether it is bounded or none of these. So now let me try to analyze this question. Suppose if you have been given this function 0, 1, 2, r, okay? If this was the function given to you, and they are saying that this is strictly increasing plus continuous. A continuous function has been given to you from this closed interval. And we have studied a theorem called boundedness theorem, or a theorem called compact set mapping to compact set. So boundedness theorem and compact set theorem says that this interval is going to be mapped to a compact set. Compact set means it's going to be mapped to a, let's say, let me call this A. So f of A is going to be compact. That means closed and bounded in real numbers. So f of A will be compact. Now if I talk about f of an is a sequence in 0, 1. That means an is a sequence that has entries from this interval. So f of an will be some subset of 0, 1. Because an is a sequence that has entries from closed interval 0, 1. So f of an, can I say, will be a subset of A? A is closed interval 0, 1. This is A. So f of an is a subset of A. So if f of an is a subset of A, and the image of this set is compact, f of A is compact. So A is closed and bounded. F of an will also be what? Bounded?
Yes.
F of an will also be a bounded set. and it might not be, it might not be closed, but it will be bounded. So f of a, the range set of this set, closed interval 0, 1, is compact. So that means f of an is bounded. And when I talk about the range set of f of an, small set, sorry, I need to just do this small an, right? So this f of an is a subset of a, and this set, if I apply f on a on f, I mean f on a, then this is a compact set. Okay, so this means that f of an will also be compact, not necessarily compact, but this will be bounded set because it will be a subset of a compact set, right? Because a is compact, and if I apply f on a, this is compact, and f of an is a subset of a compact set. So, a subset of a compact set need not be closed. Okay, it need not be closed and bounded both. It need not be closed plus bounded, but it is sure that it will be a bounded set, because subset of a bounded set will always be bounded. So what I got is that f of an, they asked me f of an, about this f of an, this will always be bounded, need not be closed, but this will always be bounded. So the second option will satisfy. And when second option is correct, fourth option is itself wrong, because I have got one option as correct option. So in the second option, I used what? The boundedness theorem or the compactness theorem. This was, I think, maybe Jam's question or Tiffer's question. This was a nice question. Okay. Can we move on to the next question? Okay. Now I want you to think about if a continuous set maps a compact set, continuous function maps a compact set to a compact set, does it map a closed set to a closed set?
No,
It
ma'am.
might be or it might not be correct. Think about counter examples or think about some proofs that you can get. Someone is saying no. Okay, let's wait for some seconds. If anybody tries to think and get some idea. Okay, who said no?
I have a counter example that fx define on closed on open infinity 1 by x. Closed on open one is closed set.
Closed
but,
one, open
the image
infinity two.
R.
Can you repeat? Your voice is
R
not,
defined
was
by
not
fx
clear.
equal to 1 by
Yes. Domain is
closed one open infinity
fx is equals
defined 1 by x.
1 by x. Okay.
1 by x. The range would be
1 by x, right?
open 0. Then range would be open 0 closed 1, and that
Open
is not
0,
closed.
closed 1. And this is correct? Open 0, closed 1.
No.
Okay.
Codomain is R.
Codomain is R. Okay, that's fine. We can also write this way. Codomain is R. And you are saying that range of f will be equal to open 0, closed 1.
Open 0 closed 1, and that is not
Yes.
closed.
That is not closed. So let's try to analyze this if it's correct. See, you have a domain from 1 to open infinity. So whenever you're trying to, the graph of this, function, from closed 1 to infinity, it will be like this. 1 will be here and it will go up to infinity. So you'll have from 1 up to open 0. Yes. So the range of f will be, since this is a monotonic function, you can just apply, you can just put x is equals to this and x approaching to infinity in, f of x, and then you can just get the range of f. For monotonic functions, it is very easy to find the range. So this is the range of this function, but this is not closed. So you have an example that was continuous. Yes, it was a continuous function in this particular domain, but the range of this function did not come out to be closed. So continuous function does not guarantee that a closed set will be mapped to a closed set. Okay, but a continuous function, does a continuous function guarantees that a bounded set will be mapped to bounded set? This is also a good question. And with this question, I want to move on to this question. This is a question from CSIR Net. Don't be scared if you're a BSc student. This is a very easy question. CSIR Net's question. Try to solve this question.
Ma'am, can you discuss the above theorem once more? Above question.
Once more, what I need to discuss? What the closeness?
Yes.
Okay.
Here the function considered from the domain is 1, infinity.
Yes.
Is it closed?
Yes, this domain is closed. What is a closed domain? What is a closed set? We need to think about. So closed set is the set which has all of its limit points inside itself. So when I talk about this set, all of its limit points are closed 1 to infinity. Every point after 1 and 1 will be its limit point, and this set contains all of its limit points. So that means that this is a closed set, right? Don't confuse yourself with the idea of boundedness. We are just talking about closeness. We don't care about boundedness now. What is a closed set? Yes, if it contains all of its limit points. So the domain was closed. Now when we find out the range with the help of this function, which was already continuous in this domain, if this function, you're thinking that it will not be continuous, it will not be continuous only on x equal to 0, which is not a part of this domain. So the range of f came out to be this. But this is not a closed set because 0 is a limit point of this set, but it is not contained in it. That's why I said that we took a closed set, but the range of f we got was not closed. Okay. Now let's talk about this question. I hope if it's clear to you. If anybody is having any doubts, you can just ask. Feel free to ask. Try to solve this question. In between, you will see a lot of Hindi, but try to find your options. How many of them you think are correct? How many of them you think are wrong?
Ma'am, option 2 is wrong, I think.
Option 2 is wrong. Okay.
I think 2 and
One
3
answer I
and 4 are
got,
correct.
2 is wrong. I don't know if it's correct or not. Well,
I think
inverse
3 and 4 are correct.
3 and 4 are correct. Someone is saying. Inverse image of any set. I don't know if I'll be able to write this definition correctly. Inverse image of any set will be the set of all those points such that f of x belongs to A.
And for option 4, I have a
Counter.
counter.
Okay, we'll discuss about it. Keep your counters to yourself until we get to the point. And giving you 1 more minute to think. It's not necessary that you solve for all the options, but try to do as many as you can, because we are, we have limited time, so I can give you 5 or 10 minutes. But yeah, try to use your head for just 1 or 2 at least. function. This is the definition of inverse image. That if you take any subset from the codomain, and if you want to find the inverse image of that set from codomain, subset from codomain, then you have to collect for all those points from the domain that such that f of x belongs to A. Yes. Any answers? Any more answers? We'll discuss now if you don't. So the only condition that they have given you in this question is that f is continuous from reals to reals. Nothing more. Nothing more. Okay. F is continuous from R to R. Okay. So now let's talk about the first option. If A is closed, f of A is closed. So we talked about this option earlier, and you all know that this option will not be correct. So this is not a correct option because we have, we can also take some example like FR to R, f of x equal to e to the power x. And if you take, A is equals to reals, then f of A is going to be, let's say, like this. E to the power x has the range set like this, which is again not closed. Okay. So now this option is also not correct. I give you some other example. We discussed some other example earlier. I gave you a new example now. You see counter examples. Finding counter examples is not so difficult when you have a bunch of examples with yourself. Try to think about polynomials, trigonometric functions, inverse trigonometric functions, exponential functions, things like that. If you have a bunch of examples with you, you won't get confused in finding the counter examples. For the second option, someone was saying that it is wrong. Yes, I want to know why is it wrong? Do you have any answer? Otherwise, we'll discuss.
f of x is equal to x.
F of x is equals to x. Then, if A is bounded, the inverse image of A is bounded. I don't think that it will work here. F of x equal to x.
F of
0
x
to 1.
equal to 3.
F of x equal to 3.
Constant number.
And if you take, A to be, if A is bounded, okay, sorry. A is, let's say 3. Because the function is defined from reals to singleton 3. So let me take A is equals to 3. What is the inverse image of this, constant? This is a really nice example. I don't know who of you gave this, but very nice way to think. Very nice way of thinking. So inverse image of A will be, F inverse A will be R, because all the real numbers give you the answer 3. So inverse image's definition is all the points that give you this answer, So inverse image will be whole of R, because whenever you put any point from real numbers, you always get 3. So the inverse image will be whole of the real numbers. But they are not bounded, but your A was bounded, but the real numbers are not bounded. So this option is incorrect. Very nice. They are asking us the correct option, right? Yes, correct options. So first and second are not correct. Third option is, if A is closed and bounded, then f of A is closed and bounded. This is a very direct kind of thing that I shared with you, the boundedness theorem or the compact to compact relation, that if A is compact or closed and bounded, you can apply the compactness theorem that F maps compact set to compact sets. Yes, this is correct. What about the fourth option? If A is bounded, then f of A is bounded. Does a continuous
We
function?
can
Yes.
we can
The
again
fourth
use
option.
the fact that compact goes to compact, because bounded set is some subset of compact set, closed boundary interval.
Yes, but they're not given to be
Any
bounded
bounded
is more
set is
general. Compact is more specific. Okay, let me give you an
so
example.
A is bounded.
I have to have a bounded set. Okay, the function is defined from R to R. Okay. So the function has to be from R to R.
But our function is R to R.
The function is from R to R. We can take this example, right? The function has to be from R to R.
So we can use that A is bounded, then A is subset of some closed boundary interval.
A is subset of some closed and bounded interval. Yes.
And then we can use the compact goes to compact.
If A is bounded, then it need not be. Yeah, if A is bounded, then f of A is bounded. Okay. So it is a subset of the domain, which is of real numbers. And how can you say that it will be a subset of a closed set?
Is that is lying between some minus m to m.
But
We say A is bounded if there exists a m such that if a domain is domain was not R, then we can't say, because open 0 1 1 by x
yes,
is a counter.
exactly. But in such a case, you are taking a bounded subset of this domain. You're talking about a continuous function throughout the domain. So it will not have a discontinuity of any limiting kind of thing. Yes. So yeah. It will be, if A will be bounded, then by the above theorem, we can say that yes, it will be a subset of closed and bounded. Then its image will be bounded. Okay. Yes. So in this case, just a second. In this case, we have function defined from R to R, and the function, and we are given that A is a bounded set. Okay. Then we know that compact sets are mapped to compact sets. So with the help of this, I can say that this bounded set will also be mapped to a bounded set, because we have the domain of real numbers, and bounded set in this case will be a special case of closeness. So here I can say that if A is bounded, the resultant will be bounded with the help of that compact goes to compact related theorem. So fourth option in this case will be correct. Okay. Okay, so we have two options correct and two options incorrect in this case, right? So yeah. So we have another question before that. Up till now, if anyone has any doubt, you can discuss. Otherwise, we can move to this question, which is a very easy kind of question. I think this is a question of JAM.
Ma'am, can you explain that fourth option once more?
Okay. So in fourth option, you have been given a bounded set. If A is a bounded set. Yes. and the domain and the codomain that they have given is continuous. The function is continuous on the whole of R. Okay. So continuity plus boundedness. Just a second. So F is continuous from R to R, and F is continuous from R to R, and if A is given to be bounded. So in this case, I have one confusion. So whoever explained this, can you explain it again?
Okay. So A is
Yeah.
bounded. So definition of bounded set is for every x belongs to A, x should lie, there exists M such that x should lie minus M, comma M close interval.
Hmm.
So it is clear that A is a subset of close interval minus M to M. And that close interval subset of the domain, because domain is R.
Hmm. So you're saying that for all x belongs to A,
So that,
should lie from minus M to M. But it
Yeah.
need not be closed.
and that close bounded interval minus
In that case, it will be closed and bounded.
what?
Or madam, can we
Is
say
a
like that?
subset of R.
If I take the
Yes, it
Hello?
will be a subset of R. It will be a subset of closed set. Bounded and set. Yes.
yes, ma'am, if I take like this way, that suppose A is a subset of R, then I can take A is a 0, 1, okay, to satisfy this condition, not to counter example. To A is a 0, 1, and I take f of x equal to x. Then by the fixed point theorem also I can say it's make a rectangle that is closed, that is bounded throughout the whole domain, and the image is also bounded.
Fixed point theorem will be applicable. If it is closed, it will be applicable. Fixed point theorem.
Then subset is closed. No, 0, 1, if I take as a closed subset of R, that is applicable. No, I can make a rectangle over there that will be closed and bounded too. So
Okay.
automatically it gets satisfied. That is bounded as well as image also bounded.
But it's
So by that
using, it's using the concept of fixed points.
fixed point, yes.
Other than that, I wanted to use some other concept.
Ma'am,
Okay, we'll keep it on. Yeah.
A is a bounded set. So A closer will be a bounded set as well as a closed set. A closer. So image set of A closer will also be a compact set, because A closer is a compact set.
Yes. A closer will be
A
compact,
closer will definitely be a compact set, because A
and
is
a
bounded.
closer will
And,
be also compact.
yeah.
And this implies that
So A must be, A is a bounded set, then F of A must be bounded.
f of A is a subset of f of A closer. In that case, I don't know if this result is true or not. I don't remember if this condition holds or not. If this condition holds, then it will be easy to do. F of A closer. Okay, let me think about it. Till then, you solve the 27th question. This is a very easy question. Till then, I'm thinking about this question.
This is a very easy question, madam. It is actually we are making a rhombus.
Yes.
We are making a rhombus, and it is a range of f is close interval. Third is
Okay.
correct.
Okay. 27th question. Yeah.
Yeah, third is correct because it is making rhombus.
But let others try for just
Yeah.
a minute. because that's an easy one. Anyone can try this.
Yeah.
I have a little doubt regarding this result, because if we have to apply fixed point theorem, then it will be a little higher concept, because we are not covering fixed
Ma'am,
point theorem here.
is it clear now? A is a subset of.
Tell me if this result is true, because
A is a
A is a
subset.
subset.
Let I equal to minus m to m close boundary interval. Let I equal to minus m to m close boundary interval. Okay. A is a subset of I. So both side apply f.
Okay.
F of A is subset of f of I.
So this will be compact.
Now right hand side is compact set.
Right hand side is compact set,
Compact
and
set.
subset of a compact set.
Compact. Compact means
Is
close
bounded.
bounded. So any subset of bounded set is bounded.
You can think about, yes, exactly. Think about this as A is bounded means that A is a subset of any compact set. Because even if A is open, let's say A is open in the worst case, then in that case A will also still A will be a subset of some compact set, right? So if I apply F on this compact set, you know, F of A, let's say whatever this compact set, let's say this was I, F of A will be a subset of I. Again, if you apply a continuous function on a compact set, this will be a compact set. And a subset of a compact set is not always compact, but it is always bounded. That means F of A will be bounded. Why is it bounded? Because compact set is always bounded set. The subset need not be closed, you know, but the subset is always bounded. So in this way, we are saying that F of A is a bounded subset. Okay. So now this means that F of A, even in the worst case scenario, in any case, whatever A was, open, closed, or not open or not closed, F of A is bounded, because we have taken the help of a compact set. Yes, this is a correct way of explaining this. Yes, very good. Whoever explained it. So whose doubt was it?
Yes, ma'am. Now it is clear. Thank you.
So very good. This is a very easy question. Let's discuss this one now. I hope you have tried it. So in this question, we have been given a domain x, y belongs to R square, such that mod x plus mod y is less than equals to 1. And f d to R is a non-constant continuous function. Okay, you cannot take a constant continuous function. So this is a function which is non-constant and continuous. So which of the following statements are true? So they are talking about whether range is bounded, whether it is a union of open intervals, whether it is closed, or what it is. So we have seen that domain is something like this. And if you watch it carefully, this domain is nothing. But this domain is a subset of R square, which looks something like this. And it covers the inside portion and the boundary also, because they are saying that mod x plus mod y is less than equal to 1. You can easily draw this by taking the 4 cases minus x plus y is equals to 1. It is a, you know, x plus y is equals to 1 and x minus y is equals to 1. It is just a intersection of these 4 lines. Okay, so this domain is clearly compact domain. Why? Because we are in R square, and still in real numbers, closed and bounded set means compact. Compact means closed and bounded. So this is a closed and bounded set. So this is a compact set, and compact set will be mapped to a compact set. So they are asking me the range of f. So range of f will be compact. So let's say which options match. The range of f is unbounded. This is not correct. The range of f is a union of open intervals. If this is a union of open interval, it will never be compact. So this is also incorrect. The range of f is closed interval. This seems correct, but let's read the 4th option. The range of f is a union of at least 2 disjoint closed intervals. Okay, so the range should be a
Domain is also connected.
Yes, exactly.
Domain is also connected. So connected
Domain
goes
is
to
also
connected.
connected.
So any
This seems
connected
correct. And 4th
subset
option.
of
Exactly. So the domain is a connected domain, and we have also studied this theorem that connected maps to connected, right? Connected will be mapped to connected. Compact will be mapped to compact. So the domain is compact. Range needs to be compact. But here it says that range of f is a closed interval. Is it bounded? Closed interval, okay? Is it bounded or not? They haven't guaranteed.
yes, ma'am.
And here they are saying the range of f is a union of at least 2 disjoint closed intervals. It will not be correct, because if it is a connected domain, then it should go to a connected domain, right? So the range should be an interval, and this should be incorrect, because the range is, they are saying that this is a union of 2 disjoint intervals, and in that case, it will not be connected. So C option will be correct. So in one question, you can have, different kind of theorems to be applicable. So we have done like 2 questions here related to boundedness theorem, compactness, connectedness. I hope it is clear to you. So let us move on to the next one. Let's see what we have. Okay. So this is a very famous result when you are doing questions of real continuity, that if a function is from real to real and f is continuous, then this kind of set is closed and this kind of set is open. What is this set? S1 says that the set of all those points such that f of x is less than equal to 0 or it is greater than equal to 0. When you have this equality sign, this kind of set is always closed. The points which satisfies this condition is always a closed set. And S2 says the points which satisfies the condition that f of x is greater than 0 or less than 0, it is an open set. I'll give you the idea of the proof of this question. You can use the idea of sequences. You can take any limit point. If you want to prove that this set is closed, you can take any limit point of this set. And by taking any limit point, let's say L of this set, you can always find a sequence that converges to this limit point. For any limit point of a set, you can always find a sequence. And there you can continue solving for the proof of this question. We are not covering the proof because we are limited in time. And you can start doing it. If you have any doubt, you can Google it, because you'll find a lot of proofs of this, or you can follow some book. You can find these proofs wherever you want. Okay. So the next theorem, which is very important, is location of roots theorem. Location of roots theorem says if your function is continuous and it is defined on an interval, it has to be defined on an interval for this to follow. And if you say that f of a is less than 0 or f of b is greater than 0, for some point, you have functional value to be positive, and for some point you have functional value to be negative. You can always find a point between A and B. Between A and B, you can always find a point, let's say C, wherein you can say that f of C is equals to 0. And it is clear from the graph. That's how, you get the idea. Because if you have a negative point, if you have a positive point, the graph is continuous. There is a connection. As the domain is connected, you don't have to lift up your pen, and you can always, cross the x-axis. You'll always touch the x-axis, and that point where you touch the x-axis will be the root of, this function. So this is the basic idea. And the next theorem, intermediate value theorem, follows the idea of location of roots theorem. It says that if I is an interval and f is from I to R, if I is an interval and a function is defined from I to R, and let's say some points a, comma b belongs to I. Okay, and if there is, a maps to f of a, b maps to f of b, let's say there is some point, I don't know, f of a can be greater than f of b, or f of a can be less than f of b, it doesn't matter. Or a and b can have any relation. This function can be monotonic, non-monotonic, any kind of function. But if you have f of a and f of b, you can always find a point inside between this, let's say call it k, and this k will always be some value related to some c belongs to ab. K will be equal to f of c such that c belongs to a comma b. So what does this mean is, here you can also say this, k is equals to f of c where c belongs to ab. So what this means is, if you have, let's say, any graph, and you have this point a, you have this point b, you can always find, this is f of a, this is f of b. You can always find a point between this, and this will be, this point k will be related to some value here, c, okay, which lies between a and b. And why this happens is only because this function is continuous and this function is defined on an interval. Suppose this function would have been defined on natural numbers, let's say, then this condition could not be held. So when the function is defined on an interval, on a continuous, on a connected domain, then such a condition occurs that between f of a and f of b, you can always find a k which is related to some c. K takes value, the c takes value k at f, and that c lies between a and b. So the idea of this proof is very simple. I can give you a hint. You can define a function gx is equals to f of x minus a. It's also written there, and I'll share the notes, you'll get to find it. You can always define a new function gx, and you know that g of a will be less than 0 because g of a will be what? F of a minus k. And you are supposing, let's say, f of a less than f of b, and your g of b will always be greater than 0. By location of roots theorem, you can say that between a negative and positive value, you can always find a root. So let's say you found out c such that g of c is equals to 0, and when you say that g of c is equals to 0, you mean that f of c minus k, that is g of c, is equals to 0. So this means that k is equals to f of c, and that's what you wanted to prove. You can follow the idea that is shared in this question later after this class. This is a very simple idea. So you get the idea. Why I'm sharing the proof with you is because you get the idea of what connected domains means whenever you're talking in continuity. Okay, so we have covered this location of roots theorem and this intermediate value theorem and this basic theorem related to closed and open sets. Okay, so let's move on to, let's say, see if we have some questions. Okay, we have a question. Okay, before covering this question, this was asked in June 2016 in CSIR NET exam. Before covering this question, I want to ask you, what do you know about monotone functions? So monotone function is a function which is either monotonically increasing or monotonically decreasing. We have 4 types of monotone functions: monotonically increasing, monotonically decreasing, monotonically strictly increasing, monotonically strictly decreasing. So monotonically increasing functions are those functions whenever you have x less than y, you have f of x less than equals to f of y. So constant function, if you can think of, is also a monotonically increasing function. And in the similar way, if you have x greater than y, you have f of x less than equals to f of y. This is a monotonically decreasing function. Okay, constant function can also lie in the category of monotonic functions. But when you talk about monotonically strictly increasing functions or monotonically strictly decreasing functions, you cannot have this criteria. You'll have to say that monotonically strictly increasing functions, you'll have to say f of x less than f of y strictly. And for x greater than y, you'll have to say f of x less than f of y strictly. So you have this idea. Always monotone functions have this property that their limits always exist. You know, LHL and RHL will always exist. They might not be equal. It is not necessary that they are equal, but LHL will always exist. RHL will always exist. Doesn't matter they're equal or not. So it does not have a continuity of second kind. In second kind, we said that LHL might not exist or RHL might not exist. So only discontinuity monotone functions can have is a discontinuity that is called the jump discontinuity. That is, let's say, you know, the functional values do not match. So at any point C, let's say, you have RHL is equals to the functional value, but LHL is not equal to the functional value or RHL. So this kind of discontinuity you can have, jump discontinuity, this is called. RHL, okay. This is where function takes value, this is a whole. So monotone functions can only have jump discontinuities. This is what you need to know about monotone functions. Now let's move on to, okay, let's move on to another idea which is very important about monotone functions, and this is used in every exam, whether it is NET, GATE or CSIR NET, CSIR GATE or JAM. So this idea says that if you count the number of discontinuities, if you try to count the number of discontinuities of, you know, jump discontinuities, let's say, if you're counting the number of jump discontinuities of any function, any possible function in this world, you can always have at most countable of them. So they are not more than countable. You know about, I think, countable and uncountable sets. So if you're trying to count the number of discontinuities of any function, they are at most countable. Either they are not there, either they are finite, either they are infinite but countable, or they are not uncountable. They are never the kind of uncountable discontinuities. Again, you can get the idea of the proof by, you know, dividing discontinuities into different intervals, union of different open intervals. You can get the idea. The proof is a little time taking, so I'm not sharing the proof. You can always refer the proofs from the books, you know, Bartley and Papa, you can refer regarding this. So I want to ask you this question, and now this question is very clear. I've explained you every concept that if R to R, f is a function and it is a monotone function, then what is correct? F has no discontinuity, F has finitely many discontinuities, F has at most countable discontinuities, or F may have uncountable number of discontinuities. Whatever answer you have, if you're rejecting any answer, just give me counter example. A monotone function with no discontinuity.
If x equal to
Is it
box
always
x,
possible?
1,
X is equals to
box x, 1 and 2 discard.
by box X you means greatest integer.
Greatest integer function.
Yes.
Yes.
So 1 and 2 you are discarding. Okay, nice.
Ma'am, by Riemann theorem, I can say. Riemann saying that if it is monotone function, then directly that is theorem f has at most countable discontinuities.
Yes, I shared the theorem with you, but I want to know the
Okay.
amount
Discard
of counter
the
examples that you can give. Yes, for discarding, you
Okay.
should give counter examples because you cannot remember every result in exam. So you need to have
Exactly.
enough number of counter examples. That's why I'm focusing on counter example kind of learning.
Then for first it is correct. Greatest integer function is correct. Correct one for
First,
first and two.
first and two, exactly.
Okay. For fourth, wait.
It's all absolutely correct. So you won't get counter examples for this. But
You already shared a theorem.
yes, so I already shared the theorem because it's needed there. Also, fourth will not be correct because third is correct. But when you go into the proof, you will find why fourth is not correct. So the reason for fourth not being correct is that you are not going to get any counter example, no, is when you do the proof of third, you will get to know the idea of the fourth one. Why is it incorrect? So the third one is the correct answer. Okay. So what we
Means
discussed
you are
on this page,
means you are saying that when I'll try to prove the fourth one, that time I'll get a contradiction.
yes,
Correct, no? Yeah.
you're
Okay.
trying
Nice.
to prove, you can do a proof with multiple ways. If you're trying to prove fourth one, you will get, contradiction, you'll end up proving the third. But yes,
Or
you
we
will
may
prove
refer
it by,
we
if you prove it by
yes,
contradiction,
yes,
you'll get
yes.
the
Or we may refer that Riemann proof, and in that case, if I'll in place of countability, if I'll put uncountability, I'll get a contradiction definitely.
yes, exactly. Prove by contradiction. So we discussed about monotone functions. What are they? Very simple idea. But what was more important, that monotone functions have always this property that their limit exists either from the right or from the left. They might not be equal, but they always exist. And also the discontinuities, that the number of discontinuities, the number of jump discontinuities we have are at most countable. So since a monotone function, always we can always have just the jump discontinuities. So in case of monotone functions, we need to count just the number of discontinuities. Maximum discontinuities they can have is the number of jump discontinuities, and the number of jump discontinuities we discussed was countable. So third option came out to be correct. Monotone function is a very important concept while discussing continuity. So I shared it with you. Let us just spend 5 or 10 minutes more in this. Yes, this is a very important one. Very important one for most of the exams. If you know these kind of results, then you are good to go for most of the IBP questions and monotonicity questions. Okay, this is, maybe I missed something. Intermediate value property, yes. We discussed about the intermediate value theorem. What does the intermediate value theorem said? That if a function is defined from an interval to R, and if you have, like 2 points, A and B, let's say A less than B or A greater than B, doesn't really matter. And f of A is less than B or greater than, f of A is less than f of B, or f of A is greater than f of B, doesn't matter. But you can always find a point between this. Obviously, there are, infinite points between this. Let's say that point is K. If you find a point between these two, then that point will take, that point will be the functional value of some point C. That point C lies between A and B. That point C, that point K will be between f of A and f of B, and will be related to C, and C will lie between A and B. So that was intermediate value property. Intermediate value theorem said that if f is continuous, then f has intermediate value property. So this whole idea is intermediate value property. But when f is continuous, then it satisfies the intermediate value property, that for any 2 points A and B, there exists some K and things like that. Then if f is continuous, then it satisfies this property called intermediate value property. This whole first statement is called intermediate value theorem. Okay. So this property is called intermediate value property. But if f is continuous, it satisfies the intermediate value property, and this is called intermediate value theorem. Okay. So now second result says if f has intermediate value property, if f can only have second kind discontinuity. See, if a function has intermediate value property, what will be the possible structure of that function will be? If a function has intermediate value property, yes, if function has intermediate value property for any 2 points, you can always find the point which is related to some point C, right? So you can always you can only have second kind discontinuities for this kind of functions. Next up we have, if f is monotone, then f can only have jump discontinuity. This is an idea I discussed with you earlier. If a monotone function you have, you can only have jump discontinuity because the left hand limit and the right hand limit always exist. And in that case, only possibility for a discontinuity is that jump discontinuity. So second and third are basic ideas. Now fourth one is monotone and IVP. If a function satisfies monotonicity and IVP, intermediate value property, then that function can be called continuous. If a function is monotonous and it satisfies IVP, then it is continuous. Why? Because if a function is monotone, it will not have jump discontinuity. And if a function satisfies IVP, it will not have second kind discontinuity. So no possibility of jump discontinuity. So sorry. It can, if a function is monotonous, it can only have the jump discontinuity. And in this case, if it satisfies the intermediate value property, it can only have the second kind discontinuity. So monotone says that it cannot have second kind of discontinuity. IVP say that it cannot have jump discontinuity. So all the possibilities for any kind of discontinuity is cut. So the only possibility for that function left is continuity. So when these two properties come together, monotonicity and IVP, the function becomes continuous. And the last two says, if function is defined from an interval to R and if f has IVP and is 1, 1, then f is strictly monotone. Yes. If f has an intermediate value property and f is also 1, 1, then f is strictly monotone. I can give you the hint for this. Take some A, B, C, and suppose that f of A is greater than f of B, because you want to take the contradiction. You want to take the contradiction that f is not strictly monotone. You do something like this, and try to prove that, try to come up with some contradiction. You suppose something on the contrary and try to come up with a contradiction by using the intermediate value property and 1, 1ness. Well, you can get this f of A. If you go further in this, you can make two cases. F of A might be less than f of B. Just take contradiction here, f of A and f of B. F of A can be less than f of C, less than f of B, or second case can be f of C less than f of A, less than f of B. And in those two cases, if you apply intermediate value property, there will be some D such that f of C is equals to, there will be some, f of D such that our, this K thing is equal to this. And when you're saying these are 1, 1, so this means D is equal to C, but this is a contradiction to the fact that we took A less than B less than C. So D was a different point and D belonged to A comma B. So D belongs here, D belongs to, here, and C is a different point. So C and D are different, but you are saying that they are equal by 1, 1 property. So this is a contradiction, complete contradiction. So you cannot say this. So that means f is strictly monotone. So in that way, you can get the idea of this. Even if you don't get it here, you can just refer to the questions. But always remember that if a function has IVP and it is 1, 1, then it is strictly monotone. Then the next point is if f is continuous. Yes, also one thing I want to share with you. Can you say anything more than this? You know, it's f has IVP, I said. Plus I said that f is 1, 1. I said then this f is strictly monotone. So after this, if I say that f has IVP and it is 1, 1, f is strictly monotone. Now, once this result is made, I can say that f has IVP and f is strictly monotone. And with the help of these two, I told you that if a function is IVP and it is strictly monotone, it doesn't have discontinuity of any type, then it becomes continuous. So not only you can imply strict monotonicity with the help of this, but you can also imply that if a function has IVP and it is 1, 1, then it is also continuous. Now let's come to the last point, which is just this. If a function is continuous and it is 1, 1, then it is strictly monotone. How can you prove that? Very easy. If a function is continuous, then obviously it has IVP. Result number 1 said. If f is continuous, then f has IVP. So I'm saying that if f is continuous, then it has IVP. And if it has IVP and it is 1, 1, then I just proved that it is strictly monotone by 5. So by 5, I can say that f is strictly monotone. So this is a corollary of 5. Okay, so these results are confused when you read them for the first time, but very interesting and very important when you come up with more questions. So I want to know the answer of this question. This is a easy question. Tell me what will be the answer of this question. What will be the answer and why will it be the answer? This was asked in GATE 2016. And this is the last question. The class.
Continuous.
Okay. Why continuous?
It is strictly increasing.
It is strictly increasing. That means they have given you that this is a monotone function. Yes. Monotonicity is one
Image
thing
is
that
connected. Monotone and the image is connected. That means intervals. So these two implies continuous because any monotone function cannot have any monotone function has a property that it always left hand and right hand limit exist. And that limit is left hand limit is supremum and right hand limit is infimum at that point.
Yes.
And image is intervals. These two implies continuous. We can prove that.
Okay. So somewhere we can say that it somewhere satisfies the intermediate value property because of it being an interval, the image being an interval. So also monotonicity says that limit always exists. LHL and RHL always exists. Right? So with the help of above results that we saw, monotonicity and somewhere intermediate value property, we can say that function F is correct. So fourth option will be correct. Okay. So all these other options are talking about discontinuity. These are incorrect. Okay, so this was all.
Also we can say the since f of s is connected intervals, that means it satisfied IVC.
Yes,
Because
exactly.
if you take f of a and f of b and k lies between that f of a and f of b, since this is interval, so there exists x as that f of x equal to k, and you already said that a monotone and IVC implies a continuous.
Yes, exactly. Monotone and IVP, that's what I told you here, that you can directly use results also, that monotone and IVP. Because Fs is connected, it will satisfy. Fs is connected, it will be kind of an interval. Connected in real analysis means some interval. So it will be an interval. So it will satisfy the intermediate value property, and with the help of 1 and 2, we saw the above results. You can say monotone plus IVP implies continuity. Okay, so this was our, which result was it? Yeah, this was the fourth result.
Ma'am, I kind of have a doubt with that question, which where we had that on the fourth option we had a doubt, no, regarding that for a function which is continuous from R to R, and then for a set which which is bounded, then f of a will be bounded or not. So can we prove it with this statement? Because since a is bounded, then for a function also continuous in R to R, then there kind of will be have this maximum and minimum values for that function, right?
If A is bounded, you will have a supremum and infimum for that function.
In R, so
Yes.
so f of a will be bounded, right?
How? A is
Because
bounded, right?
f is continuous and a is and it is from R to R, and so for a is bounded, then there should be an in maximum and lower value, so there will be minimum and maximum value for that function.
Yes.
And values must lie in between that, right? So it should be bounded, right?
But these values, let's say A is some open interval. So what are you saying?
But the values will be bounded for f of a, right?
Sorry?
But then the values will lie in between a certain interval, so that it could always only be bounded. It cannot exceed that boundedness, right?
Yes.
But
F of A
it
is
may not
bounded.
increasing function or decreasing function.
No, if it is increasing or decreasing, then it can only be a constant function, right? Except for because it is a continuous function, so it can only be a constant or either increasing or even if it is not increasing or decreasing, still it should have
If
an
it is
top
not
value.
monotone, then
It has, if you take a consider sin x or cos x, it is an increasing or decreasing in complete interval, but still it has that value on top and down, right? So it can only stay inside that. So f of a is bounded by that.
We can say that A is bounded. A can have maximum and minimum values inside R. Means that superior and infimum values. But how can you say about f of A?
Because f is continuous, so for f is continuous in the whole R, so that function cannot have anything outside R. Because if it
That I don't think is a correct justification.
if we already assume then f of a has a supremum income, that means we claim that already that f of a is bounded, and we are going to prove that.
But then you don't have any other possibilities, do we?
You'll have to justify. If you're saying that f of A is bounded, you'll have to somewhere justify that. I know that the value f of A is bounded. What does it mean? You have to prove that it attains its bounds, right? F of A is bounded means it must have supremum or infimum. So F of A can be something like this, possibly. F of A could be something like this. How can you justify that F of A is not like this? Sorry. F of A could be something like this. Thing is to justify that it is not like this.
Because it is continuous. No, A is bounded, right?
A is bounded, right?
Then it will be it won't be continuous in the whole interval of R. It is continuous in the whole interval. So
Mhm.
it can never reach infinity or negative infinity, something like that, or just can't have any values different. It can only be a line or something like a function.
Yeah, you can say that. Due to continuity, it won't take some infinite values or anything. Limiting values won't be infinite. So F of A will also be a subset of R.
Ma'am, let supremum of A is C.
It just doesn't.
Let C is the supremum of A. Let C is the supremum of A.
So C is the supremum of A.
A Kodo, ma'am.
Voice is lagging. I don't know if it's an issue with my internet.
Madam, other way around, if the thing is that if we give the counter example for every option except fourth one, then that will be better for us. Hello.
I can give this. I know it is not a complete justification, but I just found a way just to try to make fourth example, and we need to check the fourth one also, right? You can
Exactly,
just
sir. Exactly, sir. I'm saying that if we give them, means the thing is that uh, either we can prove that fourth one is correct with the help of hypothesis. Otherwise, we will counterly give the counter example for other three. Those are left, means 1, 2, 3 options. Or to them, we will give the counter example. Then we can easily satisfy ourselves.
But
And
this
if you wanted to prove, then we can also.
question is multiple select question. So you cannot, in this question, 2 options were correct. So you cannot take out all the examples and cancel out the possibilities of other options. This was a multiple select question. So in such
Then we have to
questions,
prove that both.
justify each
We
and
have to
every.
prove both. Yes, justify each and every statement.
Yes, exactly.
I want to clear the question. Is my justification clear? And I think, can I possibly assume that D was also correct by this justification, or just I need to go for further more justification?
You might be correct, but I think your justification needs more clarity. I'll think about it in this way that you're saying, but it needs more clarity.
Okay,
But
thank you, ma'am.
the way we did, I think it is clear to everyone. It has many ways, obviously, it has many ways. I didn't actually, when I was solving this question, I didn't actually look at R to R. So I solved it other way. So that was my mistake. So please come up with some justification. We can also discuss in the group. And if I come up with something, I'll share it. So every question has many possibilities, not just that we stick to one justification. So it's okay if you're thinking about something else. But right now you don't have a strong reason for that. Okay.
Ma'am, if we take x in the interval 0 to open pi by 2 and consider the function tan x, will it be a counterexample?
But that tan x is not defined from R to R, no? That is defined from R minus 2n plus 1 pi by 2 to R. So that
Oh.
is tan x is not a justified example here.
Okay, ma'am. Thank you.
Hmm. Yes, sir.
Could you go by counter positive, like suppose that it is not true?
Suppose? Yeah.
Suppose your function is not continuous, since it is monotone, the only kind of discontinuity you have is jump discontinuity, then somehow contradict that f of s is connected.
So you're supposing that f is not continuous. And
It is given that it is strictly increasing, therefore the kind of discontinuity you have is the jump discontinuity.
let me just there it is not given that it is strictly increasing or something. This is the question actually. You were discussing this previous
Oh,
question.
I'm sorry, I'm sorry.
Yes, yes. This is the only thing that they have given. So I'm done. We can have this interactive session again.
Ma'am, first of all, just tell me. The
Hmm.
thing is that whenever I'm trying to study for night exam, no, I'm go on studying the real, go on studying the complex, and go on studying. I'm solving the questions too, but I'm not doing the partial differential equation, or you can say differential equation, and means that I applied, but I'm not doing, and that's why I think so. I'm not clearing it. Such a kind of things are there because even though you study a lot of me solving the many problems of that real analysis, we are getting lag behind while exam because sometimes it will not be click the click it on that time of a real because the real is like that way to other it is chance. So I think so that and how to revise means how to go for study means how to study. That is first of all my question: how to study for this exam?
First of all, you asked about that you are not able to go for the applied portion. Maybe it is not that motivating for you. But I will say that whenever you are studying, you should divide your week, into pure and applied portion, because both of them are important for this exam. Because applied portion will get you marks, pure portion will get you the knowledge and everything. It will get you marks, but applied portion is very important for me personally. I did the applied portion, and applied portion, if you're doing it in the long way, I mean, if you're solving the questions by the long method, it will not help. So try to come up with some easy tricks and short tricks. If I have time in the future, I mean, 2 or 3 months, I don't think I have time to arrange classes. Otherwise, if I arrange those classes for PD, I'll give you some short tricks, which are very helpful in these exams. So whenever you're studying for applied, you should study for short tricks, because yes, you're correct that you will not always be accompanied with only the pure portion. It has to be very, very strong to think about counter examples and results and everything all at one go, because there are chances of making mistakes in at least one of the options in part C. So that's correct. Do divide your week in pure and applied portion, as the pure portion is more, so you can give like 70-30 weightage. 70% of your week should be for pure portion, 30% of your week should be for the applied portion. And for one day in a week, do not study, just revise. Okay, it could be Saturday, it could be Sunday. For that one day in a week, just revise the concepts, just go over what you have done and just try to recall and revise, and which is very important part of your preparation. You can just go and go and go. You have to look back also. So try to devote at least 8 to 10 hours in a week to your what do I say, maybe revision. Okay, so 70-30 and also 8 to 10 hours at least for revision, or one day. So that I'll say.
Oh, okay. Thank you, ma'am. Thanks a lot.
Okay.
Okay, thank you. Others?
Hello.
Yeah.
Hello, everyone. My name is Bhavin, and this is the first time I'm attending this online meet, and it wonderful session. The best part I found was that you gave examples of each and every theorem. And ma'am, I wanted to ask you that as I'm starting the preparation after 2 years, there has been a gap, so my concepts are not that clear in real analysis. So can you recommend some book or something that so I can clear my basics according with your lectures? It would be really helpful for me.
I would recommend reading maybe some Indian authors' book. S.K. Mappa is one of the good choices. Or yes, S.K. Mappa is good choices. I won't recommend you 2 or 3 books. S.K. Mappa. I'll write it in the chat. It is a good book with enough number of examples, because whenever you are reading, you don't have enough number of examples and proofs and everything. But if you have a gap and you want to start again, S.K. Mappa would be a great book to start with. If you find yourself comfortable with this book, you can also move to Bartley or some other book. I think you know about Bartley. So I always recommend Bartley. It's a great book. It's have a